We're going to look at acids and bases and their strengths. And what's cool about this is that we can figure out the strength of an acid or a base a lot of times due to their stability, and that stability is going to help indicate what might happen in a reaction and what might be favored or unfavored. So first big thing is making sure that we understand two major concepts of being able to identify an acid or a base. An acid gives away an H plus, it's like a proton, it's a hydronium ion, and base accepts it. Okay, so whenever we're dealing with any reaction, we have to be able to recognize this. So let's do a simple reaction here on the top of ammonia with water. Okay, and that ammonia and water is going to make this for now. Oops. So what you want to do is you want to have some pairings. So for example, this looks like that NH3 is linked to that NH4 plus, and that H2O is linked to that OH minus, right? Just based on what's happening. So if I am here to identify which one's which, let's just look at this NH3. What has happened from NH3 to NH4? Well, I have 3, now I have 4. So it gained an H. So that must be a base. So I'm going to write a B underneath it. Okay. If I go the other way, it had 3 and now 4, and now it only has 3. So if you lose one, you act like an acid, right? Here's the difference. I cannot write on the right side. This might be a review for you or might not be. Acids or bases. I have to say it's partnership. So that's actually called a conjugate acid. It's the partner to the base. So when you say conjugate acid, it's the partner to the base. What is this water doing? It went from 2 H's to 1 H. So it lost an H. So you donated an H. So that is an acid. And then vice versa, when you're going back the other direction, this must be the conjugate base. Why? Because I had 1 H, and now I have 2, so I gained. So whenever you have bases, you gain, depending on the direction. And when you have acids, you lose. Okay? So this is not something you have to memorize, this sheet, but just so you understand that when you see Ka, that's basically the strength of an acid. Okay? As you get larger Ka, you are gaining strength. So we're just making sure that we have an understanding that the acid strength is increasing here. And I guess what this is supposed to show you is, please understand that these are, look at this, the structure is the same as that, it's just losing an H. So these are actually their conjugate bases. So write Cb here instead. This is the conjugate base. It's its partner. So after an acid reacts, okay, after an acid reacts, here's my acid, it becomes the conjugate base. That's kind of what this table is showing. So I have my acids, and now I have my bases. So if I have a really strong acid, and the strength of an acid is how willing it is to drive the reaction to the right, that means that this base is going to be very weak. But here's a key thing, is right to the side of this, right, base stability. Here's the thing. The stronger something is, the more likely it's going to want to react. The weaker it is, the quote-unquote happier it is. So if you have something weak, then it's very stable. And that is what we really are talking about. We want stability. We want to reach stability. So the weaker something is, the more stable it is. Okay? So there's a couple things I want you to think about here. One, let's just cross these off right here. Let's do a different color. So here is a checklist of acid-base factors. This is so important. You're going to have to memorize this for the whole year, is that this is your priority list. So we have charge, electronegativity, and resonance. And we'll talk about this. Believe me, we'll talk about all this. But that's what we're going to utilize in a second. Please understand that resonance is going to be a tiebreaker. I will show you how we're going to apply this in a moment. So again, if I have a strong acid, just so you understand this, then that means I have a very stable base. If I have a weak acid, I have a very unstable base. And why I'm saying that is that the stronger it is, the stronger it is up here, the weaker it is here. Right? So if I have a weak acid down here, that means that the stability is low. Okay? So electronegativity, let's just remind ourselves of that quickly, is that if you're looking at the periodic table and you have these four elements right here, C, N, O, or F, and you want to put a negative on that, electronegativity is about going to the right. The negative should be on the more electronegative if the negative is on the more electronegative element, it is more stable. Okay, so I know it's a little confusing yet, but we'll get there. Just hang with me here. So let's talk about the next part here. So what are we talking about? Details of acid-base patterns to remember. Again, this is what we're just breaking down 3 ideas here. Charge, okay, if it has a charge, all else equals, if all else is equal, the cations are more acidic than neutral, and anions are more basic than neutral. So we'll see how that looks in an example. Electronegativity, again, just did it. We will do it again. If carbon is attached to any, or hydrogen is attached to any one of these, let's give an example. Okay, electronegativity moves more to the right. So if all of a sudden it loses an H, acids lose H's, right? So if each of these H's leave, okay, now I'd have a carbon with a minus, I'd have an N with a minus, and I'd have an O with a minus. Well, this is based on anion stability. Okay, I want something that's more stable. So this would be the most stable because it's the most electronegative. And it has a negative, then that would be the most stable. And you can read all through that. Again, applying it is the most important part right now. And then finally, resonance is important. And we'll talk about that, but if there's resonance, that means that you can change, your bonds move around and you have some stability, but that's going to be more of a tiebreaker. So let's look at some examples. Okay, so in the upper right here, I wrote a little something. It said acidity of parent is related to stability of the conjugate partner. Translation. What it really means is that you want to go from something that's bad, so your acid is not very stable, to something that's very good. So you want to go from this acid to this really good base. Okay? So the more stable the base is, it means the more unstable the acid was. And the reason why that is important is that it's driving the reaction to want to reach stability. So bear with me, and this will hopefully make some sense. So all these are starting out as acids. And if you're told an acid, then the product has to be a base. So that means that you have to lose an H initially because the original acted like an acid. So it would be this, NH2 with a negative because I lost an H. In this case, it had a plus, it has too many H's. So when it loses an H, it'll be all good. Now, to be stable, you actually don't want any charges on your base. But in this case, because it already had a charge here, it signifies that it's making something better on the right side. So this is based on charge. And that is my stronger acid. It's going to drive it to the right. So this, in theory, is like this is more likely going to happen faster. Okay, charges are easy to recognize. You can already see it now, but I'm going to draw it anyway. So this is what this one would look like as a product. This is what this one would look like as a product. I'm losing my H. So because of a charge, there I am again. Now, you don't have a charge. Okay, so I don't have a charge. So now what do I have to do? I have to drop down to other criteria. So let's take a look at this one. You don't know answers until you actually write the products. So I'm going to write it below here. This is what this would look like. This is what this one would look like. Okay, so they both have a negative on it. Okay, but reminder, electronegativity. Right? The more negative or more electronegative an element is, the more favored it is if it has the charge. So because oxygen has the negative on here, this would be more favored. Oh, I missed the other one. I'm sorry. So if I ranked these, in stability, this would be number 1, this would be 2, and this would be 3. Why? Because here's oxygen, here's nitrogen, here's carbon. Okay? The more electronegative it is, the more likely it should have, or the more favored and stable it would be if it has a negative charge on it. Okay? Let's keep going. Next one. I have this compound right here. I'll do this one first. Okay, this one, this is interesting, but if I draw this out, I could have this structure. But, you guys, I could also have this structure. So I have a double bond here, or a double bond here. So what is this? Well, this was based on electronegativity, sorry. What is that? That is resonance. Let's talk about that. Notice, I have a negative on an oxygen, I have a negative on an oxygen, I have a negative on an oxygen. So it's not about, they were both neutral, so charge doesn't matter. Electronegativity, it's the same, so resonance is my tiebreaker. So because this has a resonance, I choose that. Next one, same concept. This is my product. This is my product. H disappears, but why do I have to have it right there? I could also have it right here. Okay, so this will definitely be favored. Now, here's an extra question. So this is also based on resonance. Which one of these two right here would be favored, more likely favored to exist? They aren't maybe 50-50. Well, you look at electronegativity. So because of the fact that this one has the negative on the oxygen versus this one on the nitrogen, this one's probably more favored, okay? This is going to be more favored of the two resonance, and that would be your argument because of electronegativity. So let's rank these, and in fact, let's add one. So please write one extra one here. So I encourage you to pause this for a moment and try to come up with, I'll show you one of them, what the base would look like. So for example, you just get rid of an H. So that's what that would look like. So remove one H, add the charge that it would have or lack thereof, and write them all on the bottom, and then resume, and we'll talk about it. All right, so what you should have done is come up with compounds that look like this. I am just removing one H, and I'm assigning it as a negative. Why a negative? Because when you remove an H, it becomes negative. H's are positive. Okay, so based on my rules of charge, electronegativity, and resonance, which ones are my favorite? So we are ranking this 1 through 6 instead of 5. All right, so let's rank them. All right, well, first I see a charge right here. So because this has a charge, this is number 1. So because of charge. It has a charge. And honestly, you can think of it, well, when it has a charge, if it goes to neutral, it's even better. Okay, sorry, butchering that. All right, now, I don't see any other ones with charge, so now I've got to go down to electronegativity. So let's focus on electronegativity. So electronegativity says that the negative should be on the F, then the O, then the N, then the C. So what do you see? Oh, I see an F right there. So that must be my number 2. No other Fs. Okay, now what? Now I stay on electronegativity. Now is anything on an O? Is anything on an O? And oh, I do. I have 2 O's, right here and right here. Oh shoot, I have 2 of them. Well, what's my tiebreaker? Resonance. Which one could be a resonance structure? Yes, this one. Why? Because I could put the double bond here, right? could go between here, and you could go there. So once that's a 3, this has to be a 4. Okay, then what? I'm still on electronegativity. Go down to N, and there's a negative on an N right here. So that becomes my 5th strongest, and then it wraps up with the 6th. Okay, so then on the bottom it says, for the anions drawn in problem 6, rank them in terms of basicity. So now what you're doing is saying, okay, going the other direction. Which one's the strongest? Well, you guys, if this is the strongest acid right here, okay, if that's the strongest acid, this must be the weakest base. Okay, it's just the opposite. If this is really strong, the other partner has to be really weak. So they're going to be the opposites. It's just that simple. If we're going the other way. So that this would have to be 6, okay? This would have to be the strongest going back the other way, because if this is the weakest here, that means, if this is the weakest, then it's making the strongest partner, because it's not going far. Strength means how much you actually go this way. So it's not wanting to go very far this way. So that means that it's the opposite, going the other direction. Okay? So that's 1. What this would be 5, 3, 2, and a 4. Okay. So let's take a look at more. Okay, choose the more basic. More basic. So you got to remember that now this is going to grab H's, right? You're grabbing H's. You're going to gain H's. So again, this is from bad to good. Keep thinking about this. We'll discuss it as we go. Okay, so let's talk about what you're going to do. You're going to gain an H. So NH3 becomes NH4 plus, right? And this one, what is this? This is an ion. So you got to remember that this is going to come off already as an ion, and now it gains an H. That's a tough one. So which one am I doing? It's still about charge, then it's about electronegativity, then it's about resonance as a tiebreaker. So because this has a charge, that's my answer. Let's keep going here. So that's based on charge. And again, if you're like, well, I don't get this good to bad, I'd rather have something stable with no charge that's created. So that's a more stable product. So some of us, that's the way maybe you're going to think. You're going to look more at the product than the beginning part. This is again ionic. So I start with this. I'm going to gain an H. Here I'm going to gain an H. So because this had a charge to start, that's going to be a more basic compound. Okay, keep going. NH4 plus, H3O plus. Okay, which one will this be? Well, this is a hard one. So let's talk about this. If I have electronegativity, remember, it should be negative, the more negative on this side, but that means also the more positive on this side. And that's a concept here that's interesting. So this is going to be like oxygen. It's the oxygen versus the charges on the oxygen or the charges on the nitrogen. Why am I going to charge? Because I have something that's both neutral here. So I need to think about what does it mean when I have a positive. This is going to be less stable. And the reason why is that you should have, it should be more negative on an oxygen. Right? So if it's more negative on an oxygen, it should be more positive on a nitrogen because of the fact that I have oxygen here and nitrogen here. So because of that, this is actually going to be the more favored base. Okay. Do not worry so much about what you've seen with this pH. It's just a compound that we're going to have. It's just a shortcut. So let's just look at the rest of it. So I'm going to add an H, right? And in this case, I'm running out of room, but I'll write it here. All right, which one's favored? What do you think? I'll let you think about that for a second. Same concept here. Which one's favored? All right, so we're going to come back. We'll talk about it. Final part for today. Predicting the equilibrium, predicting which way it goes, okay? So this is really important. Equilibrium favors the side that has the more stable, less reactive base, okay? So I can't emphasize this enough. You're going to look at the bases because that's going to be the stability. Okay, so let's take a look at what we're looking at here. So first, you got to pair them up, guys. You got to pair them up. So I have, these are my partnerships, right? What is that H2O doing? It is losing an H. So this is an acid, right? This is a base, has to be. The partner of the acid is the conjugate base, right? And this has to be an acid. So technically conjugate base, conjugate acid. So let's talk about what we are seeing here. Is which one is the stronger acid, which one is a strong base, which way is it going to go? So I'm going to look at the bases. You're going to look at the bases. So I'm looking at both bases here. Which base is stronger? Okay, or which one's more stable? Sorry, which one's more stable? Well, they both have charge, so that doesn't matter. But I look at the electronegativity. So oxygen should have the negative, right? Not nitrogen. Oxygen should. If I write those all out again, oxygen should be more negative than hydrogen. So what you do is you think, okay, fine. That means that the reaction is more favored going this direction. Why? Because this is the more stable base. So because of that, this is considered the weak base. And then this has to be the weak acid. So this has to be the strong acid, and this has to be the strong base. All right. Hang with me. Let's look at it, another one here quickly. So again, here is the partnerships. All right, this has to be an, what is this doing? This is an acid, right? So this must be the base. So automatically the partnerships have to be base, and this has to be acid. So which base is more stable? Well, they both have a negative on the oxygen, but why can't I draw it like this? So based on resonance, this is the more stable base. So the more stable base means that there's a stronger acid creating that. So that means that this has to be driving it to the left. The strong acid is always going to go to the more stable base, okay? Strong acid to the more stable base. So this is more stable, this is less stable. Just as an example. Okay, so there's a lot being said here, but the stronger acid makes the weaker base. The weaker acid makes a stronger base. Got to know that. So what we want is you always want to make the weaker base. The weaker base is more stable. Okay, that's where we're trying to head. And that really is the key. Okay? So if you can identify which anion is more stable, you can predict the direction the reaction will go. So, final question for you is, can H3O negative deprotonate oxygen? Well, let's look at that. So first, let's write it all out. We get H, this is what it's asking. Deprotonate means that it'll take away an H from it. So here's water. And now I'm wondering, can it go, here's the question, can it go this direction? So I would become CH4 because it's taking away an H and it's making that. So let's talk about it. What am I looking at? I'm trying to find the base. So which one's which? First, that links with that. This links with that. Okay. Secondly, this is a what? Acid or base? It's a base. Why? It's gaining an H, right? You gain an H. You have 4, you had 3. The minute I write base, this has to be an acid. The partner of the base has to be a conjugate acid, and this has to be the conjugate base. So now what am I doing? I'm looking at these right here, the bases. Which base is more stable? Okay, they both have charge, so that's not the case. But one has a negative on an O, the other has a negative on the C. So which one is better? Well, this is more stable. So what does that mean? That means that the reaction is going to be driven to the right. So the answer is yes, it can deprotonate. It's going to take an H and add on to it because it is more favored. This is the favored compound to be created. All right, we're going to work on a worksheet, and hopefully as we keep applying it, it will start to make more sense.